9.35, they gave us a couple of reactions, and so they don't give us the products of the reactions, but they ask us to balance it, so we'll have to predict what the products are. The only reaction that we talked about where I might expect you to predict what the products are would be an acid-base reaction. So looking at these reactants that are given, the first one I have HC2H3O2. And that's going to react with KOH. So we talked about how to recognize when a molecule is an acid versus when it's a base. An acid will have, either will be one of the strong acids on the formula sheet, or if it's a weak acid, it may have this carboxylic acid grouping of atoms that we talked about recognizing. And this specific hydrogen here is the one that would be donated as an H+, if that were to react as an acid. We also said sometimes in the formula, if the H is shown first in the formula for the compound, then that H atom is probably acidic, and that would be possibly given away as an H+. We also talked about how to recognize a base. Our most commonly used bases have a metal joined with an OH minus. And so that's an ionic bond. And the OH minus, because it has 3 lone pairs and only 1 bond, that formal negative is on the oxygen, and that allows it to attract a hydrogen that would be leaving electrons behind and going off as a positive. So to predict what's going to happen, I identify this as an acid and this as a base, and I say the base, the part that's actually basic, is the OH minus. So that's the base. The base is going to grab this H+, and it will bond with that H+. So now instead of having 1 H, it will have 2. And when it starts off negative, if it picks up a plus from that H, it will become neutral. And the other product will be this acid without the H+, so that's just going to be C2H3O2. And if it was neutral but it lost a plus, now it has an overall net negative. I also have the K+, which is just a spectator because it's already completely stable with a positive charge in a noble gas configuration. It's not going to be doing anything. It's not going to be forming any, breaking any bonds or losing or gaining electrons. It's just there to keep the charge balanced. So if I want, I can put that over here next to the negative charge where it would be maybe most attracted. So that is the way to predict the products. If we're interested in the ionic and net ionic equation, that would be separating, the ionic equation would be separating charged particles that are aqueous. So this molecule here is a molecule. It's molecular. It doesn't have any charges. So if I were to write the ionic equation, I wouldn't separate anything there, because in the ionic equation I'm just recognizing that if anything has a charge and it starts off aqueous, if they're charges, they're going to separate from one another. But if there are no charges and it's held by covalent bonds, they still should mostly stay together. The KOH is going to, if it's aqueous to begin with though, that means that I have K+ separated from and surrounded by water molecules, and the OH minus separated from that. Then on the product side, I'll form water, which will not, so this is the water, which will not have a charge and will also not separate because it's held by shared electrons, not by formal charge attractions. But then the 2 ions here the C2H3O2 minus will be separated from the K plus. So then the net ionic would be to cancel out anything that appears on both sides that is not really undergoing a change, and so that would be the potassium starting off surrounded by water, it ends up surrounded by water, it's not really doing anything. So I would exclude that, I would cancel out and exclude it from the net ionic equation. So overall, what's really happening is the OH minus is the key reactant. It's grabbing this hydrogen to make water, and what's left over of the other molecule once the hydrogen is gone is really what focuses on what's actually happening in the reaction. If we look at B, we have a similar reaction, but in B we have H2CO3, and so that has two hydrogens written at the beginning of the formula, implying that it's diprotic, or it has the ability to give away two of those H pluses. So when that reacts with KOH, not KOH, NaOH, to predict the products here, I would probably predict that both of these hydrogens would be given away. But each OH minus can only really pick up one to make a stable water molecule. So if I make a water, initially that would only be able to pick up one of the hydrogens from the H2CO3, and I could recognize that I'd be left with HCO3 minus. If that were still acidic, the HCO3 minus could then react with another NaOH, and since NaOH is a strong base, it usually picks up all the H pluses that are available. We've said anything that joins a metal with an OH minus is a strong base, not because of the metal, but because the OH minus, when it has a full negative charge, it's unstable. It's a small atom, it's not very balanced in charge. It has a negative, it needs to pick up an H plus to balance out its formal charge and become more stable. So that can still pick up another hydrogen to make another water, and now I have CO3 2 minus. Each of these produces an Na plus as well, but that's just really a spectator ion. So in this example, when I recognize that both of those are happening, and since OH minus is strong, these arrows are going to be primarily to the right, or almost 100% toward the product side. So I shouldn't have any reactants left at the end. So my products are two waters, a CO3 2 minus, and two NAs. So I am also producing this HCO3 minus, but then that goes away in the second step. And since everything is shifting to the right, the second reaction pulls the CO3 minus and reacts it completely because of the OH minus being so strong. So when I think about the full reaction here, I can cancel this HCO3 minus since it appears on both sides. And what I have is a balanced reaction is two NaOHs to produce two waters and Na2CO3. So that would be the molecular equation. The ionic equation would be just to write the same thing, but to separate anything that's charged, because we know if it's soluble in water, it's dissolving, the charges separate. So I don't have any charges here, so nothing would separate. Here I would separate the two NAs from the two OHs. the water molecules don't separate. But over here I should separate the two Na pluses from the CO3 2 minus. And then the net ionic would be to recognize that any ion or substance that's not changing whatsoever is not really relevant to focusing on what's actually happening chemically. So I can cancel that out, and the net ionic equation would just show what's really the base, which is the OH minus, and what's really the acid reacting to produce the products of that acid-base reaction. So ultimately, what do I have? I have an acid that has the ability to lose two H pluses and become less positively charged by 2 units of charge. And I have an OH minus, actually I have 2 OH minuses that have the ability to pick up 2 H pluses, and so that's why I end up with 2 waters, because each OH minus is picking up an H plus, and so that net ionic equation shows that without any clutter of showing any spectator ions, even though we know that they're there. Questions about that? Okay, let's look at the last one, because I know this is the type of question that students some students have a lot of trouble with on exams. So we'll look at part C here before we move on to another example. So here I have HNO3, and this one you should recognize on your formula sheet is a strong acid. So when I dissolve that in water, that is going to donate an H plus to anything it comes in contact with. And when I put that with BaOH2, I recognize that as a +2, because barium needs to lose 2 electrons to make a noble gas configuration, and each OH minus will have a negative. And so an OH minus is a strong base. So what if I have an OH minus like connected to a carbon or something like that? Is that OH a strong base? No, it's only strong because the oxygen of an OH minus has 3 lone pairs, and that's too many electrons for its nucleus to balance. That creates a negative formal charge. That's what makes it unstable. If the oxygen is sharing the electrons and only has 2 lone pairs and 2 bonds, that's not unstable. That's very stable, so that's not going to be a strong base. A strong acid or base means it's very unstable, it's very reactive. It needs to either pick up an H plus if it's a base or donate an H plus if it's an acid. So just because you see an OH doesn't mean it's a strong base. When you can recognize that the OH has 3 lone pairs because whatever it's connected to cannot share any electrons with it, like a metal that already has a noble gas configuration it can't share because it would break its noble gas configuration, then you recognize the OH as a strong base. So here I have a strong acid and a strong base, and so those two are going to react 100%. There isn't going to be anything left. So the OH minus is going to pick up an H, that's going to make a water. I'll have a barium, and I'll have an NO3. But then, as always, I do have to balance it. So I do recognize that here I've got 3 plus 2, 5 oxygens on the right. I only have 4. 3 plus 1. So I needed 2 here to get 5 oxygens on both sides. But now I've got 4 hydrogens on the right and only 3 on the left. Right? I've got 2 hydrogens here and only 1 here. So I need another hydrogen. Now I've got 4 hydrogens on both sides. But now I've got 2 NO3 groups on this side and only 1 on the other side. So I can make 2 of those to balance that out. If you don't like that, because we said never to change the subscripts, you can also show these as being separated, because they are separated, because they're ions and they're in water, and so you could just put the 2 here if you want. That would be perfectly correct. Also correct would be to show the molecular equation for that, which would be to show the ions connected together. Even though everything's dissolved in water, we know the ions are not connected together, but if you wanted to show that, it would look like this. So if I'm going to put the Ba and the NO3 together into a compound, that would be the way to show that I have two NO3s. The ionic equation would show all the ions separated. So here I have a molecular substance, it's not going to be separated. Here I have ions, so I want to show them separated. Water is not going to break up, it's not ionic. Here the barium and the two NO3s would be separated. And then the net ionic would be just canceling out the barium because it's a spectator ion, it's not undergoing any changes. And so I have the 2HNO3 plus 2OH to produce two waters and two NO3 minuses. In this case, you can actually reduce all of the numbers here to 1, since everything's a 2 to 2 to 2 to 2 ratio. It's the same as a 1 to 1 to 1 to 1 ratio. But it would be okay to write it like that, or to change all those 2's to 1s would also be acceptable. So the key there is to be able to recognize when you have two molecules that are reacting and you don't know what the products are going to be, to recognize which molecule is the acid, which is the base, because the acid will always take one of it or more of its H pluses and put that on the base, and then the product will result from a simple transfer of an H plus from the acid to the base. And all the time on the exam, students always make this question more complicated than it is. I'm not changing how the NO3 is connected, right? We didn't talk about any reactions where I expect you to predict the products except acid-base reaction. I'm not going to give you like an NO3 and expect you to predict how the nitrogen and the oxygen are going to break up. That's not anything we talked about. What we talked about was an acid losing an H plus and putting the H plus onto the base. That's it. Just transfer an H plus from the acid to the base. And you draw what the products become after that transfer, and you've got the answer.